All right, so today we're going to talk about heaps, which is our last data structure for the course. Heaps are basically we visualize them as trees, even though the implementation that we usually do is not trees. And the motivation here is that binary search trees are not necessarily balanced. You can make them balanced, and in fact, that's probably a subject for Computer Science 3. One of the classic balanced binary search trees are called AVL trees, right? So for example, suppose that you have a skewed tree. What I'll do is here, I'll just go 10, 20, and 30, right? You don't like this because it's not balanced, right? It's way skewed to the right. So what you can do is you can imagine that this is sitting on a hill, right? And then what you can do is you can take this and you can drag it up along the hill, and what you end up with is 20 at the top, and then 10 is on the other side of the hill now, and 30 is now over here, and it's been rebalanced, right? If it were skewed the other way, then you can pull it across the hill the other way. If it looks something like this, where you've got, say, I won't even bother with numbers now. If it's skewed zigzaggy like this, it's skewed to the right and then it's to the left, you can still rebalance this by doing a rotation here and then a rotation here. So if this is A, B, C, then the first rotation would end up with being A, and now C is out here and B is down here. And now you've got the same rotation as before, where you just have to pull it across the hill. And it ends up with being A down here, and then C up here, and B down here, right? So in other words, there are ways to rebalance a binary search tree. We won't get into that, though. Those are called AVL trees. AVL is just the first letter of the people that came up with it, or of their last names. But we're going to look at our heaps. Heaps are a little bit different, right? Again, binary search trees in general might be order n for their depth, which kills your efficiency on everything. But again, you can have balanced binary search trees. AVL trees are one, but there's also 2, 3 trees, or generally what are called B trees. Those are used in a lot of database systems. There's red-black trees, et cetera, et cetera. There's like at least 24 different balanced binary search trees. And they all guarantee that the depth is going to be logarithmic. So you can do that. But our solution for the rest of the time in this course is going to be a heap data structure. It's a binary tree that has the following properties. And before I give you those properties, remember what a heap is from Computer Science 1? In contrast to a stack is a nice stack of dishes, right? Organized, all together, contiguous. What does a heap bring to mind, though? What is the memory heap? It's less organized, it's more fragmented, it's larger, right? It's less efficient, right? And if you want to imagine it as a pile of stuff, what happens when you throw, usually we call it like a heap of garbage or a heap of clothes or something. You want to add something to the heap, you throw it on top of the heap, and it doesn't necessarily stay on top of the heap. It could roll down because this is a big giant pile of unorganized stuff. Well, our heaps are going to be organized with the following 2 properties. First of all, it's going to be full. That is, every child is going to be present up into on every level up until possibly the last one at the deepest level. But at that level, they're all going to be full to the left. So visually, what it looks like here is a binary tree, right? It's no longer a binary search tree, by the way, but a binary tree that either looks like this. It is completely full, or it could be that it's full, but not the last level, but it's going to be full to the left, to the left, excuse me, not to the right. There we go. Right. In other words, there's not going to be any gaps. All of the nodes are going to be present here until the final node here, and then none of those nodes are going to be present in that level. Right. So that gives us that the depth of this heap is going to be logarithmic. This is called the fullness property, and the fullness property guarantees that the depth is going to be logarithmic. Right? The second property is that it satisfies the heap property. The key of every node is less than both of its children. This is what we call a min heap. All right? You could go with a max heap and then just flip this definition. But in practice, what you're going to be doing is you're going to be programming this stuff with comparators, and you'll only have one implementation. We'll call that the min heap. And then if you want to flip it, then just change your comparator so that that the comparator is reversed instead. So what does the heap property mean? Again, we've got a key k here, and we've got these values a and b, and A is greater, or let's say that it's a min heap, so K is less than A, and K is less than B, and both of these. Now, is that saying that there's a relationship between A and B? No, right? We can't exploit basic search on this thing because we don't have the binary search tree property. Instead, we only have a min heap property. Looking at a much larger example here, I'm going to use the same topology of that tree before. Oh no, it's not, I can't use the same topology anymore. It wasn't full. But here's a min heap. Okay. Look at any one of these nodes, say 50, and it is greater than both of its children. 30 is greater than both 40 and 80 here. 60 is both greater than 90 and 63. It is full. Every single node is available is present at every single level except for the last level, and it's full to the left. Right? We don't have gaps here. If I were to insert another node right here, whatever that happens to be, that would not be a heap anymore because it no longer satisfies the fullness property. Okay? Now, why do we call them min heaps? What's at the very top? The min, right, in this case, right? Because if it were a max heap, the max would be at the top. But in this case, the min, 1 up here, is at the top. And again, can we exploit this for general searching or sorting or not sorting, but general searching or arbitrary insert or delete? Nope. Why? What happens if you wanted to find 95? Well, let's go with the different one. What happens if you wanted to find 72? If you tried to apply the binary search tree property, what would happen? You'd go right because 72 is greater than 1. But is it over here at all? Nope, it's over here. What ends up happening is that you have to use pre-order, post-order, or BFS or something like that in order to do a general search. So we're not shopping for a general search data structure here. If you want that, use a binary search tree. Instead, this is going to have its own applications. Okay? So again, our observations. It is not a general purpose data structure. Otherwise, generally searching it would be order n. The minimum element is always at the root. Awesome. And the fullness property, as I said before, guarantees that the depth is going to be logarithmic. So if we can come up with some operations that are proportional to the depth, then we've achieved at least part of our goal. Right? They're going to be efficient. Those two operations are going to be as follows. The first one is get and remove the minimum element. And the second one is just simply add an element. Right? Now, like I said before, if it's a heap and you just want to add something, it's not necessarily going to end up on the top. It's going to roll down and end up somewhere in the heap. We're going to get and remove the minimum element. In other words, you can, give me the minimum, give me the next minimum, give me the next minimum. This is going to have applications for priority queues and sorting, right? And we'll see that at the end here. But in any case, this ends up being another restricted access data structure, just like a stack, just like a queue. As long as you use it for the intended purpose and then you use it in the way that it's supposed to be used, everything is going to be efficient. What we need to do is we need to figure out these two basic operations. Get and remove the minimum element. Okay? So let's come over here and let's try a couple of things. First of all, I'm going to remove it. Right? And I'm going to put it off to the side here so that I can return it eventually. So here's my result. Right? But now I've left a gap here. Okay? So my first inclination is to look at both of its children. Right? And if I want to preserve the minimum heap property, what would I put up here? 5, the minimum, right? That would then end up meaning that 5 is now gone. Right? All right, well, if it worked one time, let's do it a second time. Which one of these could I promote up so that it would preserve the minimum heap property? 50. Right. Well, that leaves another gap. 50 is now gone. Which one of those could I promote up to preserve the minimum heap property? 53. And at that point, now I've realized why this is not a good idea. Right? The min heap property is certainly satisfied, but is the fullness property satisfied? Nope, I've got a gap now. All right, reverse. All right. I still want to delete it and save it off so that I can, return that value. But instead of trying to satisfy the minimum heat property, let's try to satisfy first the fullness property. Right? That means that I want to make sure that there are no gaps anywhere except for possibly the last level. And that means that I would then end up promoting 63 instead. 63 is up here. And then I would end up deleting 63. And that entire node is now gone. Right? The fullness property is satisfied. But is the heat property satisfied? No. Okay. Let's do that what we tried to do the first time. And let's just swap things. Right? Looking at both of its children here, which one would I promote up to the top now? Still 5. It's too thick. Right. There we go. I would swap these out. Swap. Right. And I would end up with 5 at the top and 63 down here. Oops. 5 is now at the top. 63 is here. Right. Is the heat property satisfied now? The min heat property? Nope. I need to go ahead and swap out 50 and 63. Now 50 is up here and 63 is down here. Is the heat property satisfied now? Nope. Swap it with its minimum child. And so in this case, it's going to be 53, and 63 is now bubbled on down to the bottom. Just like if you have a heap of garbage and you throw something on the top, it then trickles down. Sometimes it stays at the top. Sometimes it trickles all the way down to the base of the heap. Sometimes it trickles down to the middle of the heap somewhere. You just need to make sure that you're going you stop when the min heap property is satisfied. Right? Okay. So there is how you get and remove the minimum element. Right? You save off the root in order to return it. Right? Oops. There we go. You replace the root with the last element. Okay, and I'm going to put that into quotation marks for now, because how do I get to the last element? Right? That's it was kind of a given that I could do that. Right? It depends on how you implement it. Right? In other words, the lowest element all the way to the right. Then the process that we just went through was called heapify or heap fix. Right? We need to fix the heap. We swap the element with the minimum of its left or right child until either the heap property is satisfied, or we reach a leaf node, at which case we stop. Right? And guess what? This is all proportional to the depth. So, since the depth is definitely logarithmic, and of course this again makes the assumption that you have free access to the last node, right? Then everything is going to be efficient. Right? By the way, is it at all apparent the way that I've drawn this tree, how you can get to the last node? Right? From the root here? Well, we can see, we should go to the left, and then right, and there it is. We can see that because we can visualize this and immediately understand it. But you can't tell a computer that. Right? What if it was over here in the right subtree instead? In other words, we had children here, children here, children here. Right? Now the last one is over here in the right subtree, right? And we'd have to go all the way over there. How can we find it? Other than doing a pre-order traversal to find the one at the lowest level all the way to the left. I don't know how yet. All right? We'll figure that out though. Okay? But assuming that we have free access to the last node, then this is pretty straightforward. What about adding an element? And again, remember, what we're going to do is we're going to preserve the fullness property first. That's our priority. We can always heapify or fix it later. So what if I wanted to add a new element here? Say, I don't know, add 10. Okay. 10's not already in there, right? Yeah, no, it's not. Right? So if I preserve the fullness property first, that means that I would insert it here as a left child of 53. Right? Because that's the next gap, right? I would not insert it here starting at the root, because do I need to go left or right? I don't know. Where's the next available slot? Is it in the left subtree or the right subtree? And I don't know how to do that yet. So assuming that we can just jump to this location, I'm going to add it as the new child. But the fullness property is satisfied, but the min heat property is not satisfied. So all we have to do is swap, but in the other direction. We're going to work our way up here now instead. So this becomes 10, and this becomes 53. The heat property is still not satisfied because 10 is less than 50. So let's go ahead and swap them again. and 50 is now down here, and 10 is right here. And is the fullness property, or is the min heat property now satisfied? Yeah, because if I swap 5 and 10, 10 would be greater than 5, and it doesn't work anymore. If I inserted, instead of 10, if I had inserted 0, it would have bubbled its way all the way up to the top to become the new minimum, guaranteeing that the minimum is always going to be at that root. Okay? All right, great. So that's how we insert stuff. We can add stuff. And once again, it's going to be proportional to the depth. Again, assuming that we can have access to that last spot, the next available spot at the deepest level all the way to the left, we add it there. Then we heapify upwards. We swap with the parent all the way up the tree until the min heap property is satisfied, or in this case, we reach the root because we're now going upwards instead. Once again, it is proportional to the depth. And because of the fullness property, it's going to be order log n. Right? But again, that assumption, this assumes that you have free access to the next available element. Right? Okay. I'm going to show you one implementation. Actually, before I do that, what I'll do is I'll say, yes, given a tree implementation, what you can do is you can start at the root, and then you can go what you can do is you can do some math. As long as you know the number of nodes, right, and the depth, actually you don't even need to know the number of nodes, you just need to know the depth, then you can determine whether or not the gap or the next element is either in the left subtree or the right subtree. Why? Do you remember? We already did the math. Do you remember it? How many are there in a full tree on the first level? 1. How many are there in the second level? 2. How many are there in the third level? 4, right? So if I had n, I could tell what the depth is. And then what I could do is I could say, well, using some math here, at depth d minus 1, there are 2 to the d minus 1 plus 1 minus 1 nodes. So what I can tell you is there's that many nodes, and if I take out that off of that of the total number of nodes, that tells me how many nodes are in the last level here. And if that's less than or equal to 1/2 of 2 to the, what would it be, n plus 1 minus 1, right? Then I know that the gap is over here. If it's greater, then I know that the gap is over here on this side. I can repeat that math over and over and over again to find the actual last node there. If you want the full details, read the book, because I painstakingly went through all the details in the book, but I'm not going to do it here. Instead, what I'm going to do is I'm going to show you how it's actually implemented in practice, right? Because we don't actually use trees, like a node and a left subtree and a left child and a right child. Instead, what we use is something very, very basic, an array, right? Okay. What we're going to do is we're going to ignore an index. We're going to ignore the first index just because the math works out a little bit better. Let me come back over here to my heap over here, and let me show you how you can store this in an array. All right, here's my array. Here's my index 0. We're going to waste that one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and dot, dot, dot. Right? What I'm going to do is I'm going to store the node at index 1. Then I'm going to go 5 and 30. Then I'm going to go 50 and 55 and 40 and 80. Basically, I'm writing it down in what order? The first level, left to right. Second level, third level, left to right, etc., etc. What order was that? It wasn't pre-order traversal. It wasn't post-order traversal. It was that other one, breadth first search, BFS. All right. So 80, then 60, then what else? 53. All right, and 72, and 70. All right, and then dot, dot, dot. We still have to treat this like a tree, though, because when I heapify, I want to look at the parent, or when I heapify downwards, I want to look at the left child or the right child. Right? So let's try to discern a pattern here. Let's take 30, for example. 30, right? How could I find its left child or its right child? Well, its left child is over here, and its right child is right next to it. So how could I jump over here and how could I jump over here purely based on indexing? So if 30 is at index 3, right? Where's its left child? Is at index 6, and its right child is at index 7. Right? Okay, let's look at another example. What about 50 here? 50 is at index 4. Where's its left child? Which is 60. It's going to be right here. Right. Where's its right child? Right next door. Right? At 8 and 9. So do we start to see a pattern here? What if I had a node U at index I? Right? Where is its left child? 2i. Where is its right child? 2i plus 1. Right? Where's its parent? Yep, I divided by 2. And careful, it could be 5 divided by 2, which is 2.5. Is that a correct index? Nope. Yep. Just take the floor there. Let's see if that works. All right. What was this, 53? I need to go back to the parent. So 9 divided by 2, floor, that's going to be 4. That takes me back right there. Right? Works perfectly. If it was 8 divided by 4, then that takes me back to, or divided by 2. 8 divided by 2, that takes me back to 4 right there too. Right? Very, very clever way of storing a tree as an array. And you can still go to the parent, you can go to the left child, you can go to the right child. Why the hell didn't we do that for binary search trees? 1, 2, 3, ... 1 million. There's a skewed binary search tree. How big does my array have to be to hold that? 2 to the 1 million or so. Right? And there ain't enough RAM in this world. In fact, there ain't enough atoms in this universe to store that. Right? How many atoms are there in the universe? 2 to the what? 120 or so atoms in the. I guess it would be 10, whatever. So let's just say 2 to the 200, less than 2 to the 200. Right? And that ain't happening. Right? So there's your answer. Binary search trees have to have nodes because you don't have enough memory to store them like this. Why can we do it with a heap though? Because we have a guarantee on the fullness property. There are no gaps. If I were to take this, in fact, let's make it even a little bit smaller here. Let's make it just 4. There we go. What would the array look like? At index 1 would be 1. Where's its right child? It's at 2 times 1 plus 1, so it'd be 3 over here. There's 2. And 2 times 3 plus 1 would be way over here at 7. There's 3. And then 2 times 7 plus 1, that would be at 15. Right? Do you see that the gaps are becoming exponentially larger? Right? And what would be stored in this array right here? Nothing. Right? You'd be wasting a whole bunch of space to do it like this. Right? But we can do it with a heap because we have a guarantee on its fullness property. Awesome. All right. All right. So again, the trick here is that the element stored at index I has a left child at 2i and a right child at 2i plus 1, and its parent at I divided by 2 with a floor. Right? That doesn't look like great LaTeX, but whatever. Let's try left. 4? No, okay. I don't know why. That looks ugly though. Anyway, that's why we burned index 0, by the way, because it just doesn't look right with everything else. It would end up being 2i minus 1 and 2i, and then you'd have to screw around with the floor there. It'd be like I plus 1 divided by 2 divided by 4. It'd make it look ugly, right? Random access means that you can walk along the tree effectively. Right? All you have to do is compute the index offset which you want it, etc. Now this solves our original problem. Remember I said that we got free access to the first and last? Right? Well, keeping track of the size n means that you have access to the last element. Where is it? Index n. Right? And the next available slot is going to be at n plus 1. Let's see if that's true. Right? So where is the last element? How many elements are in this tree, in this heap, excuse me? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Right? So where's 63 in all this? Well, I know that its parent is at index 8, so it would be at 16 plus 1, right? At index 17, matches. Where's the next available slot here, the left child of 53? At n plus 1, 18. Right? So my problem up above was solved. I always have free access to the last element in order to swap it with the first element. And I always have access to the next available slot because I'm keeping track of the actual size. Now that takes me back to array-based lists. What happens when we've filled it up? Well, now you've got to extend it and copy things over. But hopefully that's not a very common operation, not one that's done a lot. Right? All right, let's see. So implementation, question mark? Right. So could we do this in Java? Yeah. Check out lab 15, right? Because it's kind of boring. In fact, it's so boring that if you do, what does an implementation look like in Python? Have you ever done heaps in Python? Let's go ahead and pull it up. Python heap. Right. Heap queue. All right. Where is heap? Yeah. There's a heapify method, and there's like a heap push and heap pop, right? You can add something to the heap. You can take the minimum element off the heap. But guess what? There is no implementation. All they do is use lists, right? In other words, an array. So all they're doing is, there isn't really even a heap implementation. They're just saying, you've got a list already, just use it, right? Pass it into this heapify, and pass it into this heap push and heap pop, and we'll take care of it for you, right? As long as it's a heap, right? So what would it look like in Java? Well, all it would be is an array-based list inside of a heap, and then you have this add and this push. You have this add method, and you have this get and remove min element, and everything is done in terms of the array instead, right? Meaning that when you swap two things, because they're out of order, that just means that you end up swapping two things based on their index instead, right? So it's kind of boring, right? So check out lab 15 because we did it for you, right? But what I want to talk about is applications. Applications, all right? Our first application is going to be an efficient priority queue. Why is it an efficient priority queue? Yep, minimum is always at the top. Minimum or max priority is always at the top, right? You can get and remove it with order log n. Log n. There we go. Right? And what about putting stuff in? Enqueuing something is also order log n. Except that now it's more like a priority queue now. Right? The priority queue that I showed you before, or that I visualized before, I did it in terms of line jumpers. So suppose that you had a linked list implementation of a priority queue, which probably most of you are doing for your final assignment 7, right? So it's 10, 20, 30, 40, 50, whatever, right? And you want to insert 42. You start at the head here, right? And you go, nope, go to the back of the line, go to the back of the line, go to the back of the line. Oh, no, you have a higher priority here. Go ahead and insert it right here. That would end up being order n, right? Because what if you had the lowest priority possible? You'd end up being at the end of the list here. Or even like a mid priority, and you'd end up having to be in the middle somewhere. And by the way, it doesn't get any better if it's an array, because you eventually need to make room for it. What's going to happen? You're going to shift everything down, right? But here it is efficient because it's more like a real priority queue. Have you ever gone to like Well, it's Lincoln, so there's no busy place. But have you ever gone to like a really busy delicatessen or something like that? You've seen it in a movie before, right? And they've got this big red thing up there, and it says, take a ticket. You've seen the stereotype before, right? And then what they've got, then everybody's just standing in a room, no order whatsoever, but they all have their tickets. And then they say, now serving number 42, right? And you go, oh, hey, there's my ticket. I'm next, right? And you jump to the head of the line. There's really no organization in that room, right? 42 could be standing next to 50 and number 1, right? And there's really no organization with respect to a heap either, right? Is there? Other than the heap property and the fullness property, there's no organization here. I could take 65 over here and I can move it over here and place 92 over here, and it would be the exact same heap, right? I mean, different ordering, but both properties would still be satisfied. Right? But if you use it as an efficient priority queue, then things can go in and things can come out order logarithmic on both ends, right? Okay. The other application is sorting, right? Because if I just put stuff in and take stuff out, what order is it going to be taken out in? Minimum, right? So let's write that algorithm. Right. It's going to be called heap sort. Why do you think it's called heap sort? Well, because it's using a heap, right? So my input here is going to be a collection of stuff elements. A equals A1 through AN, right? And my output is going to be A sorted. Okay? There we go. My first step here is going to be to initialize a min heap. Okay? And then what I'm going to do is I'm just going to go ahead and put everything in for each A sub I in A, H dot add A sub I. There. Then, while it's not empty, while H is not empty, right? Then A sub I, output H dot, what would it be? Remove, get min, what we'll call it. There we go. And maybe not output, but let's say A prime dot add whatever's next, and then we'll output A prime here. A prime could be just, an empty list. There we go. How dumb is that code? It's really straightforward. Dumb as in not complicated. How simple is that code? All you're doing is what? Put stuff in. And all you're doing here is what? Take out. And guess what order it's in? It's sorted. Now, remember I told you at the very beginning of the semester that there's a theme to this course, that smart data structures and dumb code are a lot better than the other way around, right? This is dumb code. It's simple code, but it is a smart data structure, right? And all you have to do is put stuff in, take stuff out, and you've sorted. That is way simpler than heaps or than a quick sort or merge sort, right? You've got this complicated hybrid recursion, et cetera, and then it switches over to insertion sort or whatever, right? That is so much easier. Is it just as efficient, though? That's the thing. Right? So let's look at an analysis here. Right? Okay. On each iteration, you are doing an operation. On iteration, say 1, there is a heap size. Now, initially, that heap size is 0. So how many comparisons do you make? To insert one element, 0, right? Because that's your new head, right? On iteration 2, however, the heap size is increased here. Now it's at 1. How many comparisons do you make now? Well, log 1, actually it's log 1 plus 1, right? But I won't consider that, okay? On the third iteration, it's now of a larger size, 2. and you make log 2 comparisons. Right? Now again, why is this log 1, log 2, etc., log 3, log 4? Because the number of operations to insert something into a heap is going to be logarithmic with respect to the size of the heap. But the size of the heap is growing here. Right? 4. The size of the heap will be 3, and you end up making log 3 comparisons. ... The last iteration here is n. The heap size is going to be n minus 1. You make log of n minus 1 comparisons. All right? What is the sum grand total of all of these things? Ignoring the 0 up there because we don't care about it. All right. Okay, let's find out. So, log of 1 plus log of 2 plus log of 3 plus ... plus log of n minus 1. Okay? You know what? Let's also simplify it because it's log of n, right? And we'll put an asterisk on that because we're not actually going to count that, but I want the math to look nicer. Log identities. Log of A plus log of B is equal to what? Log of AB. A times B. All right, let's go ahead and apply that to all of it. And this simplifies to log of 1 times 2 times 3 times 4 times ... times n. Yeah, what is that thing in this inside? Gamma function, so n factorial. Right? N factorial looks like a lot, unless you take the log of it. This is less than or equal to what? N to the n. Now, why is that the case? Well, n is your largest term here. So just replace all of these terms with n's. Right? And it's even bigger. Right? And n times n times n times n times is going to be log to n to the n. All right? What happens to that exponent? Another log identity. N log n. Hey, cool. It's order and log n. Competitive, in fact, matches merge sort, quick sort in the best case. That's for this phase right here. Guess what about this phase? It's the exact same thing, but in reverse order, because the heap size will start to diminish as you take things out. So it ends up being 2 n log n, but again, we ignore constants like that in our big O analysis. Right? So we've achieved what we've achieved an efficient sorting algorithm, right? All you're doing is put stuff in, take stuff out. Magically sorted, right? And it's going to be order, n log n. There we go. In fact, here's a secret. When I get man q sort, right. I'm on Mac right now, so this is a BSD, Linux, Unix, whatever you want to. It's not really. I don't know. Not Linux. It's a Unix variant. It's BSD. All right, there we go. Good old q sort. Tell me about q sort. I just did the man pages for q sort. Right. What is it actually? Heap sort, right? There is a merge sort. There is a merge sort. I believe that though, if you read the documentation here, that the q sort is actually it just calls heap sort appropriately. I think that could maybe that's changed, but our functions of an implementation. Oh no, okay, looks like it is, right? But it doesn't have to be. You could, of course, write your own distribution of C where your q sort is actually calling heap sort because you don't want to have to worry about the details of quick sort. Right? And I think that some of them do. But heap sort is in the same standard package now, at least with BSD, with my C, as quick sort, q sort. Right? So it ends up being, I like parentheses. I don't know about you, but I like parentheses around my ends there. Right? All right. So we've come full circle, and that is the theme of the course. That smart data structures and dumb code are a lot better than the other way around. We have maybe 5 minutes here. We can go ahead and see what it looks like in Java. Let's just go over here to demo. All right. Remember that priority queue? Priority queue of, say, integer. Right. PQ is equal to new. Ah, darn it. Priority queue. Queue. I'm going to have to import this. I don't remember. Nope. Import this. Is it a interface? Yeah, no, it's an actual implementation. Good, good. Let's find out what it is, though. Here you go. This implementation provides order log n. Yeah. It is not synchronized. All right, fine. Let's just look at the actual code here. All right. Hey, there we go. What is it? It's an array-based priority queue. It's basically a heap, like I just talked about. We keep track of the size. That tells you that you can find the next gap. It tells you that you can find the last element, right? And then you've got all the rest of the stuff here, right? But otherwise, if you put stuff in, say, I don't know, list of integers numbers is equal to list.of 10, 20, 30, just random numbers here. Single numbers, there we go. 9, 4, and here's my heap sort algorithm. For integer and x in numbers, right? PQ dot, is it add? Yep, x. Put stuff in, right? While PQ dot is empty, while it's not empty, take stuff out. And in this case, I'm just going to print it. PQ dot, what is it? Pull. Yeah, I should have done offer, but there we go. And those random numbers are now sorted. Did I have 2 2s? Yeah, I did. Right. 2, 2, 3, 4, 6, 7, 8, 10, and 30. Right. And it was all going to be log n for each one of those operations. There's your heap sort algorithm. All right. Any questions? Otherwise, that's the end of the course. What we're going to do on Monday is we'll have a course retrospective, but we'll just go ahead and cancel Wednesday and Friday in favor of next week. Remember, is your resubmission week. That one and only one assignment can be resubmitted. You have to go to help hours to get it checked off. Also, remember that the course evaluation is open, and whatever the response rate is by Friday of Dead Week, that's everybody's bonus. And then the last bonus is we're dropping your last lab, but still do the last lab. It's easy. It's based on binary search trees. Right? We're dropping your lowest lab is what I meant, right? Not your last lab. Right? So if you got like a 0 or you got like an 8 out of 10, 20 or something like that, or you missed one, that's fine. We'll drop that lowest one. That'll be all automatic in Canvas. All right? No questions? Yeah, go ahead. I thought it was Friday. All right, then we will change that. The course retrospective is on Friday, and then we won't have class at all next week. There we go. Why did I think it feels like a Friday? But, there you go. Thank you.